Okay, today we have a problem. In one type of state lottery, 5 distinct numbers are picked from 1, 2, 3, etc. all the way to 40 uniformly at random. A. Describe the sample space omega and probability measure p to model this experiment. And B. What is the probability that out of the 5 picked numbers, exactly 3 will be even? I think it would be a good exercise for you to pause the video and try this out yourself. Recall that a sample space is the set of possible outcomes of the lottery, and the probability measure essentially assigns a probability to each possible outcome. Okay, so let's get started. So first, I need to describe my sample space omega. So this is the set of tuplets of 5 different numbers which are picked from the set 1 through 40, but they must be distinct. So one could enumerate my 5 choices like so, and this belongs to the set 1, 2, 3, all the way up to 40 to the power 5, where raising to the power is with respect to the Cartesian product. So a set to some power is just that set Cartesian product with itself, in this case 5 times. And then we want to add the condition so such that xi is not equal to xj for all I not equal to j. I and j belonging to the index set 1, 2, 3, 4, 5. Okay. So this is just how I would do it on first try. I think there might be a simpler or better way of writing this, but essentially I just take the tuplets of possible lottery numbers and then I specify this additional condition where no 2 of these entries are allowed to be, no 2 distinct entries are allowed to be equal. So this encodes the information that all these lottery numbers have to be different. Okay, then to encode a probability, well, we're assuming a uniform at random probability. So we're assuming that essentially every lottery number has an equal likelihood of being chosen, which is probably not realistic in real life, but who knows? I don't want to attack the lottery system right now. So we need to determine, to put a probability measure on this, we essentially need to determine the size of this set, and then whatever the size of this set is, we're going to set our probability measure to be uniformly 1 over the size of that set, okay? So we'll see that done in a second. So let's determine the cardinality of omega. So the cardinality of omega is, well, let's just choose the first lottery number first. When I choose the first lottery number, I have 40 different choices. Then I choose the second lottery number. In choosing the second lottery number, I have 39 choices because I'm not allowed to choose the same number twice. Similarly, once I've chosen the first 2 numbers, then to choose the next number, I have 38 remaining choices, and so on and so forth. And so we see that, that the total number of choices I can make to select a lottery number is precisely 40 times 39 times 38 times 37 times 36. Okay, and so this is the size of omega, and then my probability measure that I'm going to put on a single event, not a single event, a single outcome. remember in probability terminology or jargon, outcomes are singleton elements of this set omega, and events are subsets or collections of possible outcomes. Okay, so in this case, if I assign a probability to an outcome, so to a specific element of my total space, well, this is just going to be 1 over the cardinality of omega, where this holds for any choice of outcome in capital omega. So this is reflecting the fact that we need this probability measure to sum to 1. So the total probability of everything happening has to be 1, and the probability of each possible outcome they should all be equal. They should all be equally likely. So I'm defining the probability of each outcome to be 1 over the cardinality of the total space. All right, let me know in the comments if that doesn't make sense, and I can probably try to explain it better in the comments. All right, so now, as I've mentioned in the previous lectures, if I specify the probability on a single outcome, then that immediately determines the behavior of the probability measure on any event because of the axioms of probability measures. So if you return to exercise 1.1, you can review the axioms of probability measures and recognize that that specifying for a finite sample space, if I specify the probability of each outcome in that sample space, that's completely enough to fully specify the probability measure on the total space. Okay. All right, and so this gives me my probability, and just to be clear, this is 40, 39 times 36. Okay. Wonderful. Okay. So I might write this in a simpler form so that I can simplify my notation moving forward. So this number here, if I continued multiplying all the way down to 1, I would end up with 40 factorial. And then this number is essentially 40 factorial, and then I remove the 35 times 34 times 33 times 32, etc., all the way down to 1. So removing the tail of this number is equivalent to dividing by 35 factorial. Okay, and then in a similar fashion, if I have 1 over the size of my sample space, then this is just 35 factorial over 40 factorial. Okay. All right, so this specifies my probability and my sample space, which is what they wanted for part A. So let's move on to part B. So I'll just recall part B for you. Part B says, what is the probability that out of the 5 picked numbers, exactly 3 will be even? All right, so let's look at this event. And this event is essentially the set of possible outcomes belonging to my sample space such that exactly 3 of x1, x2, x5 are even. Okay, so we kind of need to unpack this a bit more explicitly, okay? So So if exactly 3 of these are even, then there's a few possibilities. So in case I have a few different cases. So case 1 is that x1, x2, and x3 are even, and x4, x5 are odd. Okay? And then this possibility will have a certain probability of occurring. Okay? And once we calculate the probability of this event occurring, then we can just multiply this by essentially 5 choose 2. And the reason why is because my other cases are, for example, like another case could be x1, x2, x4 even, and then x3 and x5 odd. And by symmetry, oh, actually, yeah, I should probably be a little bit careful. So, well, before I invoke symmetry here. Okay, so we might need to actually tackle this case by case. Sorry, 1 second. Okay, all right. Yeah, so let's look at this case by case. So for case 1, I have my first 3 numbers are even and my final 2 numbers are odd. So I need to figure out how many possibilities there are. So first of all, if I choose the first number to be even, there are 20 possibilities for choosing x1. And then for x2, there are then 19 possibilities. For x3, there are 18 possibilities. Since I've already chosen, I'm choosing even numbers, and so I start with 20 even numbers initially, and then as I choose even numbers, my amount declines. And then if I look at x4, yeah, so x4, all of a sudden I have 20 choices again because I have 20 odd numbers. Okay, so for x4, I now have 20 choices, and then for x5, I only have 19 remaining odd numbers, and so I have an expression of this form. So this is the we could call this the number of possible outcomes belonging to case 1. And then actually now the symmetry that I was hoping for actually does work, okay? So here's why. So let's look at like case 2, for example. So for case 2, I could have x1, let's choose it randomly, x4 and x3 be even, and then, or x3, x4 maybe, x3, x4 even, x2 and x5 odd. If I look at the number of possible outcomes belonging to case 2, first of all, note that case 2 and case 1 are disjoint. So there's no overlap between case 2 and case 1. All these outcomes are completely different outcomes. And then if I enumerate the amount of outcomes belonging to case 2, well, again, I have 20 choices for x1 being even. I have 19 choices for, or I have, sorry, I have 20 choices for x2 being odd. I have 19 choices for x3 being even. I have 18 choices for x4 being even. And then I have 19 choices for x5 being odd. Because essentially, the even numbers are kind of disjoint from the odd numbers. So when I choose out an even number, and if I choose an even number or if I choose an odd number, I'm not actually decreasing, like if I choose an even number, I'm not decreasing the amount of odd numbers that exist. And so somehow these even and odd possibilities are not hurting each other. So in other words, the order doesn't matter. So even though the order of the lottery kind of does matter, the ordering of this, the ordering of these cases, like if I choose x4 and x5 to be odd versus if I chose, for example, x2 and x5 to be odd, then no matter what, I'm going to end up with the same number of possible outcomes belonging to that case. Okay? Yeah, so then in either one of these possibilities, I have the same number of outcomes. So therefore, to count the total number of outcomes in all, I just need to determine the number of cases that I can have. And the number of cases is just the number of ways to choose 2 out of 5. Okay, so there are 5 choose 2 cases, which is 5 factorial over 3 factorial times 2 factorial possible cases. So possible ways to choose 3 elements, distinct elements, from a 5-element set. Okay. All right, so let me just make sure this is correct. Some of these probability questions get tricky, so I just want to make sure that I'm not getting the wrong answer here. Right. Yeah, so, okay, so let's leave this work here, but let's erase this. And yeah, so if I want to choose, so if I choose 3 elements of x1, x2, x3, x4, x5 to be even, okay? So how many ways are there to do this? Well, I can choose, for my first choice of my element, I have 5 choices. So 5, and then for the next choice of element, I have 4 choices. And then for the final choice of element, I have 3 choices. This is the number of ways to choose 3 elements of this set. And the order of my choice doesn't matter, okay? So for example, if I just left it with this, then I'd be overcounting because, for example, if I chose x1, x2, and x3 to be, if this was my choice of elements to be even, this is equivalent to choosing x3, x1, x2, and it's also equivalent to choosing, any permutation of these, x1, x3, x2, etc. Okay? So when I originally counted, I said, okay, I have 5 choices for the first one to be even, 4 choices for the next thing to be even, and 3 choices for the final element to be even. However, in doing so, I basically counted these choices as distinct possibilities. So x1, x2, x3 is different from x3, x1, x2 in this counting procedure. So to account for this, then I need to actually divide out by the number of ways to rearrange these 3 objects. The number of ways to rearrange these 3 objects is 3 factorial, so 3 times 2 times 1. Okay, and so this is going to be equal to 5 factorial over 3 factorial. This is the 3 factorial. The 5 factorial is 5 times 4 times 3 times 2 times 1. And then dividing out the 2 times 1, I end up with 5 choose 3. Okay? This is why we call this number 5 choose 3, because we're choosing 3 elements of a 5-element set, and order doesn't matter. So there's exactly 5 choose 3 ways of doing this. Okay? So this corresponds to, okay, so for each case, so therefore, I have 5 choose 3 possible cases, and each case has this many possible outcomes, and all of the outcomes of each case are disjoint. So this tells me that the total outcomes, number of outcomes, is going to be 20 squared times 19 squared times 18. So that's this number. This is the number of possible outcomes belonging to a single case. And then I multiply this by the number of possible cases, which is the number of possible ways to choose 3 elements of our 5-element set to be even, namely 5 choose 3. So, yeah, multiplied by 5 choose 3 here. Okay, and they want the probability of this event. So we've now calculated the total number of outcomes. So the probability of the event then is probability of the event is I simply divide the number of outcomes belonging to that event by the number of total outcomes. And remember, the number of total outcomes was 40 times 39 is 38. It's 37 times 36. Okay? And so you could clean this up. You could dress up this number a little bit. So why don't we do that? So, yeah, and yeah, this looks correct. Okay, so let's just dress up this, let's dress this up algebraically here. So 5 choose 3 is 5 factorial over 3 factorial times 2 factorial. And then this 40 multiplied down to 36 is a 40 factorial divided by a 35 factorial. So that's going to be a 40 factorial divided by a 35 factorial. So that's going to come upstairs to the numerator. And we have 3 factorial. Oh, sorry. Okay, this is going to get interesting. All right, that concludes this problem.